Hello everyone, my name is Priya. I am from BSc Chemistry Honors 6th semester and I am here to prepare a video for visually impaired students, and my topic is uses of organic and inorganic reagents in inorganic analysis. Introduction. Reagents are those compounds which are used in inorganic analysis for the detection and determination of ions and molecules. A large number of organic as well as inorganic reagents have been used for this purpose. The inorganic precipitating reagents generally precipitate the inorganic species as sprangially soluble salts or hydrous oxides. The organic precipitating agents form sprangially soluble products either through coordinate linkage or through ionic linkage between the inorganic species and the organic precipitating reagents. Advantages of using organic reagents. The advantages of using organic reagents are listed below. Number 1. They are more specific than conventional reagents under certain conditions. Because of this property, they can frequently be used to detect a single type of ion in a complex mixture. They can be more sensitive. Classical semi-micro methods of qualitative analysis will usually not detect much less than 100 grams of a substance under specific test solutions. Organic reagents, on the other hand, are capable of detecting below 10 gamma and in certain cases as little as 10 raised to power minus 3 gamma. Number 3. They can be adopted in quantitative analysis. The organic precipitates are generally insoluble in water at a given pH and can be separated, dried, and weighed. Those reactions giving colored soluble products frequently show a regular change in color intensity, which concentration of the substance under test, and so are adaptable to an accurate comparison with colors representing concentration. This is the basic idea in the branch of colorimetry. Common properties of organic reagents. Some of the common properties of organic reagents due to which these are used in inorganic analysis are given below. Number 1. Formation of colored precipitate. Organic reagents form direct characteristic color with the ions to be detected for locating endpoint, that is as indicators employed in volumetric titration. Number 2. Formation of precipitate due to difference in solubility. This may be made on the basis of a gravimetric method. Number 3. Extraction in organic solvent at controlled pH. Number 4. Masking reagents. This increases the selectivity of reagents. Number 5. Difference in volatility. Number 6. Oxidation or reduction to other valency state. Uses of organic and inorganic reagents in inorganic analysis. Number 6. Was liquids. The chemical nature of the organic reagents is important in determining the use of above mentioned properties. Advantages of organic reagents over inorganic reagents. It is due to the following properties that they are better precipitating reagents than inorganic reagents. Number 1. Selectivity. In many cases, organic reagents are somewhat specific. For example, cobalt from nickel using alpha nitroso, beta naphthol or dimethyl glycozyme, aluminium from iron using cupferron, cadmium from copper using qualendinic acid, and thiourea can be precipitated. In some cases, adjustment of the pH will often cause precipitation of one constituent alone. By changing pH and solvent conditions, one constituent after another can sometimes be quickly precipitated out. Number 2. Ease of drying. Organic reagents produce compounds that have little affinity for water and are dried easily at temperature low enough to prevent decomposition. Number 3. Co-precipitation. Lack of ionic character of organic precipitation products greatly reduces co-precipitation in most cases. For example, the co-precipitation of sodium and potassium with magnesium is much less when the latter is precipitated by 8-hydroxyquinine than when it is precipitated by phosphate or oxalate. Some exceptions in metals do occur. It has been little studied, but in some cases it is as bad as inorganic precipitants. Reagents are usually insoluble in water, therefore it is important not to add an excess of reagent. This is difficult because there is no way to tell when sufficient reagents without excess has been added. Any excess that is insoluble would add to the weight of the precipitate. Disadvantages of organic reagents. There are unfortunately disadvantages to using organic reagents. Number 1. Volatility. This is the first practical disadvantage of organic reagents because distillated compounds are non-polar. The forces between individual molecules in the crystal are not very great. Thus, some of the metallic complexes which are precipitated in analytical chemistry are appreciably volatile under 130 to 150 degrees Celsius and most decompose above this temperature. Therefore, the drying of precipitate should be done below 130 degrees Celsius to avoid decomposition. Number 2. Impurities in reagents. It is very difficult to prepare an organic reagents of the same degree of purity as, say, inorganic compounds. Impurities present in organic reagents may enter into the precipitate during the precipitation and cause undesirable reactions. For example, dimethylglycosine exists in three forms, that is alpha, beta and gamma. Of these, only the alpha form is specific for nickel. While preparing dimethylglycosine, gamma form is also formed along with the alpha form. If the precipitation is carried out with this impure dimethylglycosine, then nickel will be precipitated with some other metals because alpha form is specific for nickel, whereas gamma form can precipitate other metals also. Keto-enol isomerism in such compounds as dithiazone will cause errors in colorimetric work unless conditions are carefully selected. Number 3. Low solubility of the reagents in water. This is the greatest disadvantage which organic precipitants have in comparison with inorganic precipitants. Number 4. High molecular weight. The very high molecular weight of chillate complexes formed with metal ions reduce proportionality small errors in precipitation and weighing. Number 5. Colored compounds. Chelate compounds are often highly colored, and since they are usually soluble in organic solvents, they lend themselves to colorimetric or photometric methods of analysis. Number 6. Solubility in organic solvents. Because of their covalent nature, most metal complexes with organic reagents are soluble in non-polar solvents, chloroform being usually the best. Such solvents are used to extract the complexes for colorimetric determination, or they may be used simply for separating one element from another. Thus, the complex of cupferron with tripositive iron is very soluble in ether and chloroform, which allow one to remove large amounts of iron from solution containing Al. In these extractions, the pH must be carefully adjusted to give the desired separation. Important organic reagents. Some of the important reagents which are generally used in the identification of ions are discussed below. Number 1. Oxime C9H7ON. The structure of this reagent is given in figure 18.1. It is almost a colorless solute soluble in organic solvents and mineral acids. It gives yellow color, which may be due to the formation of quinoid structure. It was introduced by Hallam and Berg in 1927 as analytical reagent. A number of metals give coordination complexes with this reagent. Example of such metals are Mg, Zn, Cu, Cd, Pb, Al, Fe, B, Ga, Th, Zr, etc. The formation of the complex around compound with a bivalent metal ion like Zn2 positive is shown below. The quantitative estimation of the complex is carried out by drying and weighing the hydrated or anhydrous complex, or complex is ignited to oxide and then weighed. In volumetric methods, the precipitation is dissolved by filtering with hydrochloric acid and then resulting solution is titrated against standard potassium bromide solution. In spectrophotometric method, the estimation of the metal ion is carried out by measuring the optical density of the complex. The reagent has been found to be soluble for Mg and Al, etc. The reagent is a 2% solution of oxime in 2N-acetic acid. Number 2. Dimethylglycosine. The reagent was discovered by L. 1905 and was applied by O. Brunk 1907 for the determination of nickel in steel. The structure of this reagent is shown in figure 18.2. This reagent gives an insoluble red chelate with Ni2 positive ion in ammonical medium. For details, see applications of the formation of chelated complexes discussed in chapter on basic concepts of coordination chemistry. Solution of palladium salts gives characteristics yellow precipitate in diluted HCl or H2SO4, but nitrate ions. Therefore, solution of bismuth salts also give a yellow precipitate in presence of EDTA at pH 11 to 11.5. For the studies, 1% solution of the dimethylglycosine in alcohol is employed. In spectrometric method, the insoluble precipitate is extracted into chloroform which yields yellow coloration and then the optical density is measured. Number 3. Alpha nitrous or beta naphthol, also called 1-nitrous or 2-naphthol. The structure of the reagent is shown at A of figure 18.3. It is orange-brown powder having melting point of 109 degrees Celsius, soluble in organic solvents, but almost insoluble in water. The reagent is usually employed as a saturated solution in 50% acetic acid. The reagent is common for the precipitation of many metallic radicals, but it is used specifically for the detection of ferric iron, copper and cobalt with palladium and uranyl salts in slightly acidic solution. It gives insoluble colored compounds under suitable conditions. Nickel and magnesium, however, are not precipitated by this reagent. Therefore, the reagent in acidic solution is used for the separation of nickel from cobalt. The structure of the chelated complex formed by this reagent with CO3 positive ion is shown at B of figure 18.3. The reagent has also been used for the spectrometric determination of cobalt and a few other metal ions. It is also used for spot test of cobalt. Number 4. Cupferron. Cupferron exists largely not in the nitroso-hydroxo form A but in the tautometric amine oxide form B. The reagent is usually employed at a 6% aqueous solution but is most useful in strongly acidic solution. In strongly acidic solution, it precipitates Fe3, Ce3 and Bta, W4, Ga and Sn2, Cu2, etc. Precipitates should be filtered immediately after their formation because cupferron is not very stable in acidic solution. Furthermore, precipitation should be carried out in cold since the reagent is decomposed into nitrobenzene on heating. The precipitates cannot be weighed after drying but must be ignited to the corresponding oxide and then weighed. The formation of chelated complex with Cu2 positive ion can be shown as follows. Number 5. Aluminone. It is an ammonium salt of orine tricarboxylic acid. Its structure is shown in figure 18.5. It is a brownish red powder freely soluble in water. It forms brilliant colored lakes with certain metals, especially aluminium, with which it gives a bright red lake. Aluminone is a dye and it is very important reagent for spectrophotometric determination of aluminium. By adjusting pH of the test solution below 7.8, it is possible to estimate 0.005 mg of aluminium even in the presence of calcium. The reagent is prepared by dissolving 0.1 gram of the substance in 100 ml of water. Number 6. Rubanic acid, also called dithioamide. This reagent is a diamide of dithioxalic acid and is in equilibrium mixture with its tautomeric diimido form. The AC form combines with nickel, cobalt and copper to give colored water insoluble inner complex salts whose composition is shown in figure 18.6. The copper, cobalt and nickel compounds are quantitatively precipitated from strongly ammoniacal solutions. In strong mineral acid solutions, rubanic acid reacts only with certain elements of platinum salts. In addition to above, rubanic acid form colored compounds with silver, mercury, bismuth and iron. Rubanic acid is not only important as spot test reagent but also as a gravimetric and spectrometric reagents. Number 7. Rhodamine B. It is tetraethyl rhodamine and is represented by the structure of given in figure 18.7. Solution of antimony 5 salts in strong hydrochloric acid reacts with rhodamine B and the aqueous solution of the reagent changes from red to violet or blue and finally divided precipitate separates immediately or after standing. Trace amounts of antimony may be detected in the presence of large quantities obtained by means of this reagent. Small amounts of iron do not interfere. Mercury, gold, platinum are precipitated while molybdates and tungstates in acid solution give color reactions with rhodamine B similar to those given by antimony salt. The freshly prepared benzene solution of the rhodamine B is preferred to the aqueous solution. Number 8. Benzidine. Its structure is given in the margin in figure 18.8. It is a basic reagent and is employed in slightly acidic solution as dihydrochloride for the precipitation of sulfate as C12H12N2H2 whole 2 positive SO4 2 negative. The resulting precipitates may be titrated against standard alkali The important drawback of the method is the relatively high solubility of the precipitate in water and even more in dilute hydrochloric acid. It also precipitates ions like phosphate and tungstate and gives crystalline precipitate with a number of metallic ions such as silver, copper, cadmium, gold, zinc, etc. With CO3 and Ti3, benzidine yields a blue coloration in alkaline medium, which is an important spot test for the metal ions. Recently, benzidine in dilute acetic acid has been also employed as a spot test reagent for the identification of some platinum metals like osmium, iridium, and platinum. Number 9. Capron or alpha benzoin. Its structure is given in figure 18.9. It is a white crystalline solid. It is specially soluble in water but very soluble in alcohol. It also exists in isomeric beta form. Cupferron is used as a reagent for the quantitative determination of copper, molybdenum, and tungsten. Alcoholic solution of cupferron gives a green precipitate with ammoniacal solution of copper salt. Precipitation of other metals in ammoniacal medium is prevented in the presence of tartaric acid. The green precipitate is soluble in dilute mineral acids. Copper can be estimated both volumetric and gravimetrically by this reagent. The green precipitate is an inner complex whose formation can be shown as cupferron also precipitates molybdenum and vanadium ions quantitatively but in strongly acidic solution. Vanadium gives a yellow precipitate while molybdenum gives a white precipitate. Tungsten and palladium also appears to be quantitatively precipitated with alpha benzoin oxide. Figure ET and AL have recommended the use of the reagent for the detection of basicity in slightly soluble materials such as Al2O3, BaCO3, etc. Number 10. Magnesium. The structure of this reagent is given in figure 18.10. It is also called paranitrobenzene azoresorcinol. 1 to 0.5% solution in 0.25 and in NaOH is generally employed. In alkaline solution, it forms a bright blue lake with magnesium ions. The sensitivity of this test is influenced by the presence of ammonium salts, so their presence must be avoided. Number 11. Alizarin S. It is a alizarin sulfonic acid whose structure has been shown in figure 18.11. It is a dye whose sodium salt is soluble in water and is employed as an analytical reagent. Aluminium salts give a red precipitate with the violet solution of alizarin S in ammonia. This complex is an adsorption complex of aluminium with alizarin sulfonic acid. Adsorption system of this type containing metal hydroxide and a dye stuff are called lakes. Zirconium 4 forms red violet colored compounds with the reagents under the alkaline condition. Boric acid also forms brilliant red color in UV light by alizarin by H2SO4. The reagent has been employed as a spectrophotometric reagent for the above metal ion as well as for few others. Furthermore, its applicability as adsorption indicator in the titration of FeCN6 whole 4 negative MoO4 whole 2 negative has also been reported. Number 5. Nitron. Its structure is given in figure 18.12. It is a yellow solid. It is insoluble in water but dissolved in acetic acid. Its 10% solution in 5% acetic acid is generally used as a reagent. Nitron with nitrate yields a strangely soluble crystalline nitrate C20H16N4HNO3 in solution acidified with acetic or sulfuric acid. Thus, nitron is a gravimetric reagent for nitrate. Perchlorate, perrhenate, tetrafluoroborate, and tungstate also form insoluble salts and can be determined in a similar manner. Numerous other anions, including bromine, iodide, chlorate, thiocyanate, nitrate, and chromate, interfere but may easily be removed by preliminary treatment. This results in the presence of chloride. Ions are generally high possible because of co-precipitation. Number 3. Siloxime. The structure of this reagent is given in figure 18.13. It is a white crystalline solid with melting point 57 degrees Celsius, strangely soluble in water. 5% solution of this in 50% ethyl alcohol is used as a reagent. The reagent decomposes in solution and should not be kept for more than about 3 days. This gives a yellow greenish precipitate of the inner complex of copper siloxime with acetic acid solution of copper 2 positive ion. Important organic reagents. Some important inorganic precipitating reagents are listed in table 18.1. Precipitation of Al3 positive, Ca3 positive and Mg2 positive ions by liquid NH3, oxalic acid H2C2O4 and NH4 whole twice HPO4 respectively can be shown as Al2SO4 whole thrice plus 6 NH4OH gives 2 AlOH whole thrice plus 3 NH4 whole twice SO4, and this on ignite gives Al2O3 plus 2 H2O. CaCl2 plus H2C2O4 at 135 degrees Celsius gives CaC2O4 H2O plus 2 HCl, and CaC2O4 H2O at 225 degrees Celsius gives CaC2O4, and this at 450 degrees Celsius gives CaCO3, and this at 850 degrees Celsius gives CaO. MgSO4 plus NH4 whole twice HPO4 gives MgNH4PO4 6H2O plus NH4HSO4. 2MgNH4PO4 6H2O on ignite gives Mg2P2O7 plus 2NH3 plus 2H2O. Thank you.